Welcome back. This is Professor H, and today's lesson is section 5.2, Exponential Functions and Graphs. The function f of x equals a to the x, where x is a real number, and a is greater than 0, and a is not equal to 1, is called the exponential function base a. All right? So the key to note here is that the variable is an exponent. That's why it's called an exponential function. Okay, so notice y equals x squared. That is not an exponential function. This is it's the squaring function. Or it's a quadratic function, or it's a polynomial function. Okay, so the variable is the base, and then the exponent is just a constant. It's a 2. It's a square. Whereas y equals 2 to the x, this is an exponential function. Okay, so if we want to graph on both of these, y equals x squared, we know this is going to be a parabola, but let's just go through the motions here. So if we put in 0, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and then of course if we do the negatives, negative 1 squared is 1, negative 2 squared is 4, and negative 3 squared would be 9. And if we plot that, that will make a parabola. Okay, so we got 0, 0, 1, 1, negative 1, 1, 2, 4, and the mirror image, negative 2, 4, and we get this parabola. And you should be pretty comfortable with graphing y equals x squared. No big deal. Now, y equals 2 to the x, what would that look like? So, if we did y equals 2 to the x, if we did 2 to the 0, that's 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. If we did negative 1, 2 to the negative 1 is 1 half. 2 to the negative 2 is 1 fourth. 2 to the negative 3 is 1 eighth. And what we're going to get, all right, let's see. So we got 0, 1, 1, 2, 2, 4, 3, 8. Of course, then it would be 4, 16. No, it would be 4, yeah, it would be 4, 16. Negative 1, 1 half, negative 2, 1 fourth, negative 3, 1 eighth. And the thing to notice is that as we get more and more negative here, negative 4, the negative exponent is reciprocal, so it'll be 1 over 2 to the 4th, then 1 over 2 to the 5th. And what will happen is we have this asymptote. This is getting closer and closer to the x-axis as you go more and more to the negative. And then on the positive side, it's starting to explode. This is what we consider exponential growth. Okay, so that's y equals 2 to the x. Okay, so let's graph y equals 3 to the x, 4 to the x, 5 to the x, and see if we can make some generalizations after we do a few of these. So we're going to do x is 0, 1, 2, negative 1, negative 2. And remember, the base is 3. And we're taking it to the 0 power. So the exponent is the variable. So 3 to the 0, 3 to the 1, 3 squared, 3 to the negative 1, 3 negative 2. So we get 1. 3 to the 1 is 3. 3 squared is 9. 3 to the negative 1. Remember, negative is reciprocal. 3 to the negative 2. So it's 1 over 3 squared, which is 1/9. Okay, so 0, 1, 1, 3, 2, 9, negative 1, 1/3, negative 2, 1/9. And again, negative 3 would be 1/27, negative 4 would be 1 over 81. So we're getting closer and closer to 0. We're getting pretty close to 0 pretty fast. And here, now it's going to explode. And it's going to have the same general shape. Okay, and again, that's an exponential growth curve. Okay, now let's try y to the 4th. And let's do 0, 1, 2, negative 1, negative 2. And the base is 4. And then the exponent is the variable. So 4 to the 0, 4 to the 1, 4 squared, 4 negative 1, 4 negative 2. So this is going to be 1, 4, 16, which I won't plot that one, 1/4, and 1/16. Okay, so we got 0, 1, 1, 4, 2's off the chart there, negative 1 is 1/4, negative 2 is 1/16. So again, we have this asymptote here. And now, hopefully you're getting an idea, a sense of this curve. See, they all look the same so far. They all have that same shape. Just, you know, as the base gets bigger, it goes up faster. Alright, we'll just do those two. So for 5, hopefully you get the sense. And what I want you to get in your head here is basically all you have to do is do 0, 1, and negative 1. So 5 to 0 is 1, 5 to 1 would be 5, 5 to negative 1 would be 1/5. And then the idea is you're going to go 0, 1, 1, we'll pretend that's 5 just to get the idea. So we have this shape here. It's going to 0 and then exploding up. Okay, so that'd be y 5 to the x. Okay. Okay, so in general, if we have y equals a to the x and a is greater than 1, okay, that's going to give us what we call an exponential growth curve. Okay. I want you to plot these 3 points. 0 for x, 1, negative 1. And then you're going to put in whatever a is to the 0, which is 1, because anything to the 0 power is 1. A to the first, anything the first power to itself. And a to the negative 1 is the reciprocal of a. And we're basically going to get a graph that will look pretty similar to the ones we've done. So if if you do just those 3 points, that gives you, pretty much all you need to know for the graph. And then wherever A is, 1A, 0, 1, and then negative 1, 1 over A. And then we get this curve, the exponential growth curve. And so note that the domain's going to be negative infinity to infinity. And then the range is going to be 0 to infinity. And also note that there's an asymptote. It's a horizontal asymptote. Horizontal asymptote. Is the x-axis, y equals 0. Okay, so as x goes to negative infinity, the y value is going to go to 0. Okay, so that's if the base is bigger than 1, you get this exponential growth curve with all those properties. All right, now let's talk about, well, what if A is between 0 and 1? So let's graph y equals 1/2 to the x. All right, let's make our xy chart. And again, the most basic way of graphing, if you don't know what a graph looks like, is you pick numbers for x, plug it into the equation, and plot points. And you do a whole bunch until you know the shape. So let's plug in 0. 1/2 to the 0 is 1/2 to the 0 is 1. 1/2 to 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2 to the negative 1. Remember, negative 1 is reciprocal, so the reciprocal 1/2 is 2. 2 over 1, which is 2. 1/2 to the negative 2. So again, the negative is the reciprocal, and then you square it. So, the negative is reciprocal, so that's 2. 2 squared is 4. So let's see, 0, 1, 1, 1/2, 2, 1/4. If we did 3, it would be 1/8. So 1/2 cubed is 1/8. Negative 1, 2. Negative 2, 4. If we did negative 3, it would be 8. So we're going to get this curve that's actually flipped around. This is an exponential decay. So we get exponential decay. Okay, so we'll make our XY chart. 0, 1, 2, negative 1, negative 2. 2/3 to the 0 is 1. 2/3 to the first is 2/3. 2/3 squared is, then you square the top, square the bottom, so it'll be 4/9. 2/3 to the negative 1, so again it's reciprocal, so that's 3/2. 2/3 to the negative 2, so you take the reciprocal and then square it, so it'll be 9/4. We'll plot those. So we get 0, 1, 1, 2/3, 4/9 is a little less than half. And we did cube, it'd be 8/27. Negative 1, 3/2, which is 1.5. Negative 2 is 9/4, which is 2.25. If I did 3, it would be negative 3 would be 2/3 negative 3, so it'll be 3 over 2 cubed, so 27 over 8, which is 3 3/8. So right about there. So what we get is this curve. Again, this will be an exponential decay curve. And we have that asymptote going this way. Alright, so in general, just like we did with the other one, if y equals a to the x, and a is between 0 and 1, we get the exponential decay. And again, just do the 3 points. So we're going to do 0, 1, negative 1. And a to the 0 will be 1, a to the 1 will be a to the negative 1 will be 1 over a. But remember, think of that as reciprocal. So we get 0, 1, 1 over 1 and a. Now remember, a is between 0 and 1, so let's say a is there. It's a fraction, or, it's between 0 and 1. And then the reciprocal of a fraction would be somewhere up here. So we get this exponential decay curve. So it's going to do something like this. It's exponential decay. And then our domain is going to be the same. Negative infinity to infinity. And then the range is going to be the same. 0 to infinity. And then of course there's now the asymptote, still the x-axis, but it's from as x goes to positive infinity instead of negative infinity. Alright, let's graph y equals 2 times 1/3 to the x plus 3 plus 1. Now note, all our transformations from chapter 2 still hold, so still work. So let's think about our base graph. Our base graph will be y. So if I throw out all the extra stuff, y equals 1/3 to the x. That will be my base graph. Okay, so I'm going to do the 3 points, 0, 1, negative 1. So that's 1/3 to the 0 is 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. 1/3 to the negative 1, again, think reciprocal, that's 3. So my base graph is going to be 0, 1, 1, 1/3, negative 1, 3. It's going to look like this. Okay, and that's not the scale, of course, it's just to give you an idea. X, Y. And now, for my transformations, y equals 2 times 1/3 x plus 3 plus 1. The plus 3 here, we're going to shift left 3 units. The plus 1 here does it up 1 unit. So remember, I'm going to move my origin and then I'm going to plot those points from my pretend origin. And this I'm going to multiply the y coordinates by 2. Y coordinates of the base graph. You're going to multiply each y coordinate by 2. Okay? So I'm going to take my base graph, 0, 1, 1, 1/3, negative 1, 3, and I'll multiply all those y coordinates by 2. So I'm going to plot 0, 2, 1, 2/3, negative 1, 6. And I'm going to count from my pretend origin this is the way I do it. So pretend origin is negative 3, 1. Okay, so or you can just add negative 3 to each x coordinate and add 1 to the y coordinates. So you can think of it that way also. Okay, so here we go. So my pretend origin's at negative 3, 1. So negative 3, 1 is right about here. So again, this is the way I do it. So let's see here. We're going to plot 0, 2, counting from my pretend origin. So remember, I'm going to do these from the pretend origin. So 0, 2. 0, 2 would be here. 1, 2/3. So again, counting from pretend origin, 1, 2/3 would be right about there. And if I were to do 2, that would be 1/9, 2/9. We're right there. And then if I did negative 1, 6, counting from pretend origin, negative 1, 6, 1, 2, 3, 4, 5. Oops, up in my graph up here. So basically I'm going to do this. And then it's the asymptote there. So it's just going to get closer and closer to, this is my asymptote. Horizontal asymptote. Y equals 1. Because we shifted the graph up 1. So it went from the x-axis to y equals 1. Alright, so all the transformations still work. You do the same technique as we did in chapter 2 and think about the base graph and kind of follow my example there. Just rewind the tape and listen to that whole thing again. Okay, so now let's look at this function. F of x is equal to 1 plus 1 over x to the x. And let's fill out this chart. X. And then f of x, which is the expression up there. If we put in 1, 1 plus 1 over 1 to the 1, that's 2 to the 1. Which is just 2. If we get 2, we get 1 plus 1/2 squared.
Welcome back. This is Professor.
So we get 1.5 squared, which is 2.25. 3, 1 plus 1/3 cubed, which is 2.37037. 4, we get 1 plus 1/4, which is 0.25. 1.25 to the 4th power is 2.4414. And then let's skip down and start looking at 10. 1.1. 1 plus 1/10 is 1.1. And we get 2.5937. 100. 1.01 to 100 is 2.70481. I'm just punching this in my calculator. I already did it, so that's why I'm going so fast. But you can pause it and try it on your calculator. If we did 1,000, that's 1.001 to 1,000. And we punch it in our calculator, we get 2.71692. Let's jump down to 1,000,000. So that's 1.1, 2, 3, 4, 5 zeros and a 1. And then that's going to get us 2.71828, and a few other numbers. And what it turns out, as x gets larger and larger and larger, we're going to keep getting this 2.71828, and then a couple numbers back here might change. And if we could go to infinity, which we can't, but if we could, if we have 1 plus 1 over infinity, and you can raise it to the infinity power, that's actually going to equal e. Okay, so e is, we call this the limit. We'll talk about that when you go to calculus. So as you take the limit of this expression here, as x goes to infinity, you get this 2.718. So e is about 2.71828. Okay. I think there's another 28 after that. Anyway, I would like you to have memorized 2.718. Okay, so e is 2.718. So now we have, and that's called the exponential number. So if I asked you to graph y equals e to the x, do the 3 points, 0, 1, negative 1. E to the 0 is 1. E to the 1 is e, which we just said is about 2.718. And e to the negative 1 is 1 over e, which is about 0.368. Well, we'll just do 0.37. And again, so is e between 0 and 1, or is it bigger than 1? Is it going to be an exponential growth curve or an exponential decay curve? So hopefully you're saying exponential growth, because it's bigger than 1. It's 2.718, about 2.718. Right, it's an irrational number, just like pi is an irrational number. And this number was actually discovered looking at compound interest. That's one of the places where, and looking at if you compound it daily, hourly, every second, and then what would happen if you can compound it in an infinite amount of time, continuously. And then this number popped up. So 0, 1. Okay, I'm going to graph it. 0, 1, 1, 2.718 out there. 0.37, it's exponential growth curve. So we have this. That's y equals e to the 2x, or e to the x, sorry. Okay, so that's a big idea one here. All right, let's look at the compound interest formula. A equals P times the quantity 1 plus R divided by N to the NT. Okay, so A is the balance, or the amount, the account balance. P is your principal, that's the initial amount that you start with. R is your interest rate per year. N is the number of compounding periods per year, and T is in years. So the compounding periods is if you're going to compound it monthly, right? So there's 12 months in a year, so N would be 12. If you do it daily, there's 365 days in a year, so N would be 365. Okay, suppose that $7,500 is invested at 7% interest compounded monthly. A, find a function for the amount to which the investment grows after T years. So we want to write we're going to use function notation. So a of t equals the principal 1 plus r over n to the nt. So remember, monthly, there's 12 months in a year, so that's going to tell me n equals 12. Okay, so we got a of t equals principal, which is 7,500, 1 plus 0.07 divided by 12 to the 12t. And then 0.07 divided by 12 is 0.005833. It's 1.005833 to the 12t. Okay, so find the amount in the account. What does the investment grow after 1 year? So we want a of 1. So we're going to do 7,500, 1.005833 to the 12 times 1. So what you need to punch that in your calculator and work that out. So it's just 12. So 7,500 times 1.00583333. Put as many threes fit in your calculator and raise that to the 12th power. And so you'll have 8,042.18 after 1 year. So you got $542 in interest. If 6 years, so 7,500, 1.00583333 to the 12 times 6, so that's 72. So either do it in your head or make sure when you punch it in the calculator you use the parentheses. So make sure you can figure this out with your calculator. So usually in class, it would have time to help you with the calculator, but you're on your own here. 1.00583333 to the 72. And we get 11,400.79. Let's try a of 10. So 7,500, 1.00583333 to the 12 times 10, which is 120. So I'm just going to write 120. So and I got 15,072.46. So a little more than doubles in 10 years. All right, now let's look at 30 years. So what would your guess be? So in 10 years it doubled. So in 30 years, is it going to go 6 times? And the answer is no. It's going to actually grow 8 times because it's an exponential function. So 12 times 30 is 360. So we're going to do 7,500 times 1.00583333, as many threes you can fit. So you might be off, depending on how many threes you put in, you might be off in the thousandths place, or maybe even off by a penny or something. Okay, so I have 60,873.73. Let me check that one more time. Okay, yeah, I got it again. All right, so that's $60,873.73. Okay, so that concludes the lesson for 5.2. Go to My Math Lab and do your exercises there, and I'll see you next time.